Yeah. Okay, good morning, everybody. Hope you can grab a seat. Hi, welcome to UAI 2026. My name is Dan. This is Emma. We're the program co-chairs of this year's UAI. We just wanted to say welcome and hello briefly this morning before getting started with our first keynote talk. I'm going to give a very few bits of information before we get started. Many of you were already here yesterday for our first day of tutorials. We had 8 wonderful tutorials yesterday. They're listed here on the slides. Thanks so much for all the presenters from those tutorials and the attendees. I think it all went quite well. The main conference, the single track oral sessions and keynotes, starts today and lasts through Thursday. So we're going to have each day beginning with a keynote in the morning, and then starting after the coffee break, we'll have oral sessions, and then a poster session in the evening. So the only kind of minor exceptions to that is that there's going to be a town hall on Thursday afternoon. That's in the second part of the second oral session, which is a bit shorter. But besides that, everything is kind of keynotes, then oral sessions, then posters in the evening. The poster sessions on Wednesday and Thursday are hybrid, and there's an online option via GatherTown with, I think, about 100 posters online altogether. And lunch is every day on your own from 12 to 2, except Thursday it starts a little bit later. The banquet is on Wednesday evening. Oh, sorry, I forgot to update the location. It's the Orchid Cafe. It's correct here on the next slide. So the Orchid House. And so just wanted to remind everybody to bring their badge to gain entry to the banquet on Wednesday. But otherwise, yeah, just in terms of practical information, all the physical poster sessions are going to be out in that main kind of rotunda that you just walked through. If you look upstairs, there are cardboard easels, and we're going to be fastening the posters to those. And there's some spots for posters that are also in the downstairs area as well. So we're going to have all the physical poster sessions there, and the online poster sessions will be on GatherTown. The banquet I already mentioned. The Wi-Fi, there are 2 options for Wi-Fi here. There's the EduRoam, and then there's their local network, which is called Events, with the password being welcome to KIT. And then Friday, so everything between today and Thursday is going to be in this room. Friday is the workshop day, and we have 3 different workshops, and that's going to be, one of them is in this room, and the other 2 are going to be in the other 2 presentation rooms from the tutorial sessions yesterday. There's one that's all the way downstairs, that's the Rod Zal, and one that's over to my left, your right, that's the Marit Zal. So the 3 workshops will be distributed between those 3 rooms. And then finally, we just wanted to say thank you to the sponsors this year for UAI. We have Google DeepMind as the diamond sponsor, Artificial Intelligence, the journal, and then Booking.com and D.E. Shaw & Co. as sponsors as well. Is there anything else?
Yes, I guess if you are on Zoom, welcome also, and do check the schedule. It does change. We try to be kind of up to date, but do check the schedule to see if like a poster has moved that you want to see. Yeah.
That's all right. Okay, great.
Julia, we'll welcome you to the stage. So our first keynote today, or our first keynote for the conference, is Julia Stoyanovich. She is a professor of computer science and engineering at NYU, where she directs the Center for Responsible AI, and her work bridges data management, machine learning, and AI ethics, and has earned her a US Presidential Early Career Award. Today, her talk is on uncertainty in data engineering pipeline from imputation to explanation, and so please join me in welcoming Julia.
Thank you, Emma. And Dan, for the invitation. Let me just set up real quick here. I don't know what's going on, actually, with the screen. Yeah. Yeah, I don't see it on here. Oh, here, okay.
I think you're still sharing. I think they're just controlling what is seen. So I think you can just switch to your slides.
Close this, right?
Ah, perfect.
Okay. Sorry, just a moment. Okay. And the first phrase I really need to read off. Goedemorgen allemaal. Het hartelijk dank voor de eer om UAI te mogen openen. Good morning. And thank you for giving me the honor to open UAI this year. And I should say up front, I come to you from a neighboring community. My home turf is data management and responsible AI. Apologies. And I spend my time in the part of the pipeline that most machine learning papers compress into one sentence. And that sentence is, we pre-process the data. So when this community says uncertainty, I would think that you usually mean something downstream from data preprocessing. A posterior, a predictive distribution, a calibration curve, uncertainty in the model. And what I want to do with this hour is convince you that a large share of the uncertainty that actually shapes real-world outcomes happens before any model is fit. In data engineering decisions that look innocuous and simple and trivial and maybe too simple and uninteresting to even do research on, but they really impact many, many properties of the models that we train and of the ultimate decisions that we make. Examples are, and you'll see many of these examples today, which value do we impute? How do we represent our features? For example, how do we create a histogram? How do we bucketize a feature like age? And also, which random seed does the explainer draw? And does this have any impact on the explanation that happens after the model is fitted? So I'll make this argument in two parts. Part one is about missing values and why no single imputer is the best once you measure multiple properties of your model. And these are accuracy, fairness according to many definitions, as well as stability together. And I will also give you a bit of a highlight of a software that we have built that makes it easy to do some of this instrumentation and tuning. And part two is going to be about explanations, and specifically about how SHAP attributions shift with feature engineering choices and vary from run to run by pure chance. One draw from a distribution, not the truth. And the through line of my talk is going to be that data engineering should be considered a first-class source of uncertainty, and we should make it visible, measurable, and governable in the same way that this community has done for model uncertainty. How's my sound, by the way? Are you hearing me? All good? Okay. So, as Emma already mentioned when she introduced me, I direct a center at NYU called the Center for Responsible AI, or NYU RAI for short. And our mission is to make responsible AI and AI synonymous in a hopefully not too distant future. And you know, it's a pie in the sky kind of an idea, but I hope we can get there together. The way that we work on this is through a combination of essentially three pillars, and these are technology, policy or guardrails, as well as education, training, and literacy. And one thing that you will notice in my talk is that I use a lot of hand-drawn artwork. People draw these pictures. AI does not, because what fun would that be, right? I don't want to give AI a task that people really do enjoy doing. And these pieces were created for the center by several artists over the years that we've worked together, and I use them to give abstract ideas, such as bias, transparency, and accountability, a concrete visual language. And there's also a QR code here. I checked it this morning. It works. And you can take a look at our website for lots more art, and please feel free to reuse it with attribution. So I mentioned these three pillars already: technology, guardrails, education, training, and literacy. Today I will talk about technology primarily, but at the end I hope to get to also discuss some of the policy implications of uncertainty. And I really do think that this community should be engaged in these conversations about policy, about the impacts that uncertainty has in real-life deployments, in pipelines, in people's lives, really. Before I get into the technical material, I also want to pause on this slide here. RAI for Ukraine, Responsible AI for Ukraine, is a program that we launched at the Center for Responsible AI back in June 2022, together with Ukrainian Catholic University in Lviv, after the full-scale Russian invasion disrupted life in that country, in Ukraine. And you'll see the light bulb that you see on the left of the slide, the smaller version of it, on some of my research slides today. About half of the technical content of this talk actually was contributed by students, very talented students with whom I have been collaborating over the years, who live and work and study in Ukraine today. And for me, this light bulb is not just a symbol, but it's an idea, and it stands for what a research community can do. Keep intellectual life going, build community, and create conditions in which students can continue to live lives that are as normal as possible under really unbearable circumstances, ask questions, learn, and publish. And that is the spirit that I carry into the rest of this talk today. And a very small advertisement, the reason there's a QR code on here is that we are recruiting students as well as mentors and projects for the upcoming cohort of this program. We're going to kick off in September. And so if you would like to work with us, I can give you details offline during the conference. Josh here has been participating in the program. Another person is Mykola Pechenitsky, who is not here yet, but I think is known in this community as well. So please talk to both of them about their experiences. Okay, so let's get to the actual technical talk. The first part of my talk is going to draw on a line of work on what I'm calling responsible data management with many wonderful collaborators. I'm highlighting some of these papers here. I'm happy to share my slides with you, by the way, in PDF or even in Keynote with, not Keynote, but Google Slides with notes. So don't feel like you need to take photos. And I'll go into a couple of these projects in depth. Okay, so to start, let us consider my favorite character. Her name is Anne. She is a data scientist who is building a model to predict an appropriate salary for each job applicant to whom her company wants to make an offer. And her workflow is entirely standard. She splits the data, pre-processes it. At the start, she joins tables, and these tables contain self-reported demographics and employment histories, so this is important. And then she's going to fill in missing values, and this is the part that I'm highlighting here. I hope the contrast is strong enough, right? This is going to be my color palette. And then she's going to tune and validate the model. And then when she evaluates the system, she notices that there is a kind of a fairness problem here. And the problem is that the model tends to offer lower than expected salaries to people who seem to be older, who have more experience on the job. So the question here is not only whether a model is accurate overall, but also where the pipeline shows disparities and where these disparities enter the pipeline. So in this case, the disparity is that particular applicants are being underestimated, essentially. So in case that this example feels American to you, and I've gotten that feedback before from European audiences, systems like Anne's are exactly what the EU AI Act classifies as high risk in employment, including decisions about pay. And the fact that the EU AI Act talks about these systems means that they exist, right? That they are already in fairly broad use, also in Europe. And these obligations were scheduled to take effect 2 weeks ago, on August 2nd, and have been postponed to the end of 2027. So the question of whether we can trust what these pipelines do is not hypothetical here in Europe, and it's also not easy, right? I mean, it's actually very hard to comply with these obligations. So this is the motivation for the kinds of knobs that I think responsible AI should expose to technologists, like all of us here in the room, right? I mean, what can we as technologists do to try and see whether the systems are working correctly, fairly, and also whether they are stable. And this is what I'll get to very shortly. So back to Anne. Thankfully, based in part on her own lived experience, Anne has a hunch about what might be causing this disparity, and she goes back to her missing value imputation step and observes that the value of the feature number of years of experience is missing fairly frequently, and it had to have been imputed in Anne's pipeline. And at the top right here, I'm showing you the imputed values with those arrows, right? And at the bottom right, I'm showing you the actual ground truth values that somehow Anne was able to get to. And if you compare the values that were imputed and the ground truth, you will see that essentially Anne's imputation method is imputing people younger, right? And I have a quick question for you. Why might this be the case? So what Anne's pipeline is doing is it's taking the assumption that values are missing at random. This is what you're seeing here, right? They're imputed kind of around the mean. Why might it be the case that values are not missing at random here? Employment, years of experience. Years of experience is a strong proxy for age, right? This is what my picture suggests. And there's one word here to denote the issue in society that people face who are on the job market, and that issue is ageism, right? So people know that it's harder to get jobs the older you get. And because they know this, they try to hide signal that would give away their age in their applications. And so they would not say, for example, when they graduated for college, and also whether they have 20 years of experience with C++, right? I mean, things like this. But what's happening here is that because people are not disclosing this information, they're being imputed younger, and then they're being offered lower salaries than they deserve, right? So they're trying to counteract something that exists in society, and it's biting them. Make sense, this example? Okay. So in Rubin's terms, of course, this data is missing not at random. As I'm sure you all know better than me in this audience, this is the hardest case for imputation. And I'll return to it shortly, but importantly, data quality issues, including missingness, often disproportionately impact historically disadvantaged groups, right? And here I gave you an example of such a group, older people on the job market. So a technical choice, like a default imputation method that Anne took in her pipeline, can compound bias that is pre-existing in society. So let me make this a little bit more precise. In their seminal 1996 paper, Batya Friedman and Helen Nissenbaum identified 3 types of bias that can exist in computer systems, and they're represented here by a 3-headed dragon, each head for a bias type: pre-existing, technical, and emergent. Pre-existing bias has its origins in society, ageism in hiring, the very thing that applicants feared when they withheld their experience in applications. Technical bias is introduced by the system itself, by Anne's default imputer that was quietly imputing applicants younger. And emergent bias arises over time. And this is the hardest type of bias to catch and to correct because it's outside of the system. It's very often outside of our measurement. So as decisions change the world, they feed back into the system, and also insidiously they feed back into people's minds, right? So a hiring manager here is going to be getting numbers that they should offer as salaries to these applicants, and over time they will come to believe that this is what these applicants are actually worth. This is what they deserve, right? And then people don't get higher offers. They are having to settle with these numbers. They accept these ones. This goes into the data, and then that data goes back into training the model. And that's emergent bias. So here's the claim of my technical segment here, and that is that imputation is not pre-processing. It's modeling. It's modeling in the machine learning sense. It's also modeling the world. It's performative, as we say. When Anne accepted the default imputation method, she made a statistical assumption about why her data was missing, and that assumption changed her model's accuracy, fairness, and also stability. And we investigated this claim that I just made, that imputation is modeling, in a project titled Still More Shades of Null, where we developed an evaluation suite for responsible missing value imputation. We structured this work around 3 questions that mirror the order of decisions in a real pipeline. First, assumptions. What is the missingness mechanism, and is missingness during training the same as after deployment? And our contributions here are to model a rich set of missingness mechanisms going beyond Rubin's classic taxonomy in scenarios that are socially meaningful, like Anne's scenario that I just showed you. Our second piece here is imputation. Which method should we use given the nature of the missingness and the model architecture? And here we experimented with 15 imputation methods from 8 broad categories on about 30,000 pipelines. We did this systematically, and we looked at what we found. And the third component here is metrics. How do we measure whether an imputation method did well? And this is really where the devil is. It's in this detail. We measure accuracy, fairness, and stability of both the imputation itself and of the downstream prediction using a library that we built called Virny. Virny means truthful in Ukrainian. And I'll come back to Virny later in this talk. And of course, the order here matters, right? Your assumptions determine which imputers you're going to use and find appropriate, and your metrics determine which trade-offs you can see. And most evaluations in this space fix the first and the third question, and only vary the second, and we vary all 3 here. Okay, so one of the key novelties of this work is how we model missingness, and we start, of course, from Rubin's classic 1976 framework, which needs no introduction in this room, but still I like to spell out details because I don't want to lose anybody in the audience. So in my diagram here, X is the actual value, Y is the observed, Z is the cause of missingness, and R is the missingness indicator. And missing data is MCAR, missing completely at random, when missingness is unrelated to the data, like years of experience may be missing due to just a form processing error, unrelated to the applicant's other attributes or to the experience itself. Missing data is MAR, missing at random, when missingness is related to values we fully observed, but given those, not to the missing variable itself. Years of experience may be missing more frequently for applicants with less formal education, for example. And finally, MNAR, missing not at random, when missingness depends on the missing value itself, even after accounting for everything that we observe. Experience is missing more frequently when experience is high. This is the example, right? This is what Anne actually saw, because applicants worry about age discrimination. Okay. So here's the thing. Rubin's taxonomy, of course, describes pure mechanisms, and real data is rarely pure. So we go beyond it in 2 ways. First, we model mixed missingness, MCAR, MAR, and MNAR coexisting in the same data set, which is what a data integration process would usually produce. We also model missingness shift. The mechanism you trained under is not the mechanism that you deploy under. Think of Anne one more time. She trains on historical HR records where experience was missing because of how the old system recorded it. And now she's going to be running it on a new system where the primary source of missingness is actually this pre-existing bias. So this table is our scenario design. For those of you who know the graphical missing data literature, the M-graphs of Mohan and Pearl, that work tells us when recovery is possible in principle. And what we are after here is complementary, what actually happens at finite sample sizes, to a bunch of metrics, to accuracy, fairness, and stability, when these assumptions are violated in these structured ways. And we carefully designed our missingness scenarios to be socially meaningful. And here I'm showing you a scenario for the diabetes data set at error rate of 30 or missing rate of 30. We have numerical and categorical columns. For example, MAR, family diabetes history is missing more frequently for women than for men. And physical activity and sound sleep are missing more frequently for people over 40, because they don't sleep as well and they don't exercise as much, and they are embarrassed to disclose it. Yeah, so this makes sense, kind of. And these are plausible patterns, right? You can think of privacy. And the injection conditions are grounded in the data itself. This is what I'm showing at the bottom of the slide. We're looking at correlations between features on the bottom left and also at feature importance at the bottom right, right? Because if a feature does not actually drive the prediction for even some fraction of the population of the data points, then it doesn't matter what you do to it, presumably, right? Missingness is not going to matter. To evaluate imputation under these scenarios, we selected 15 methods from a bunch of categories, following taxonomies from the literature, from, I think, your literature largely, starting with deletion. And it is not a data imputation method, but this is a very common method that people use in practice. And, you know, spoiler alerts that I think you can predict is deletion is the worst thing you can do, really. And then we go all the way into deep learning methods here. And we paired each imputer with 6 model classes, from decision trees and logistic regression to all kinds of other things like neural networks and Gandalf and a deep tabular model. And we ran them on a bunch of data sets, 7 data sets spanning hiring, lending, healthcare, and education. And these are benchmark data sets in the responsible AI literature. And altogether, once again, 30,000 pipelines, right? So this is no small feat. And the natural question then is, how do we judge them, right? How do we tell what methods work and what do they really do? So we evaluate along 3 dimensions. These are accuracy, stability, and fairness. And on both sides of the pipeline, we look at the results of the imputation itself and also at the performance of the downstream model. So for imputation quality, this is the middle column here, how well did we reconstruct the missing values, given the ground truth, right? Because this is all purely synthetic. I hope this was clear. We inject missingness according to the scenarios that we define. And so we use some of the standard metrics here, F1, RMSE, KL divergence between true and imputed values. And because reconstruction quality can differ across groups, we also measure group differences here. And this is what I'm calling fairness, right? So this is, are you predicting equally well according to your metrics for older and younger people, for example? And for the model, F1, and then also stability and uncertainty, label stability, I'll talk about these immediately, and standard deviation of predictions. And we also take a decomposition into aleatoric and epistemic uncertainty that I will tell you about in just a slide. And we make all of this precise. So here we measure, once again, accuracy, we measure stability and uncertainty, and for fairness, we measure disparities, both in various accuracy metrics and also instability across groups. And the reason that we measure both sides, both imputation quality and model performance, this is a question. Does getting the imputation right guarantee getting the model right? How many of you think that the answer is yes? Yeah, not really, unfortunately. Usually it's no. Sometimes there are, of course, connections, but usually you need to measure performance at both ends. So to build intuition for these measures, let me switch tasks for a moment. And here I'm going to be predicting a loan, whether a loan will be repaid. 1 means it will, and 0 means it won't, right? And I have 3 applicants again, Anne, Bob, and Kat. And instead of 1 model, we score each applicant with 3 models. They are denoted in colors here, yellow, purple, and black, trained on slightly different samples of the same data. And for Anne, all 3 models agree with high confidence that she will not repay, so she doesn't get the loan. And whatever we think of that decision, it's a stable decision, right? Everybody agrees. For Bob, all 3 models hover around 1/2. The models agree, but each is unsure because the case itself is ambiguous here. And this is aleatoric uncertainty. It lives in the data, and more data will not make it go away. And I'm sorry if I'm boring you, but this is the teacher in me. I need to really dot the I's and cross the T's. So finally, for Kat, the models disagree. Yellow says no, black says yes, purple says maybe. The problem is not ambiguity in this case, but it's inconsistency between the models, and this is epistemic uncertainty. It lives in the model, and it can hopefully be reduced with more data or a different model class. Now, I know that this distinction is second nature in this room, but the reason that I bring it up is what comes next, that we turn each of these into a measurable property of the pipeline, once again, per individual and per demographic group at benchmark scale. So machinery here will not surprise you. We train M models on bootstrap samples of the same data and score the same test point for all of them. And everything we measure from here is a property of this approximating ensemble. The first measure is label stability, agreement in the predicted labels across the ensemble. If all M models assign the same label, then label stability is 1. If they split down the middle, then it's 0. And notice that Bob and Cat both come out unstable, but of course for different reasons, and this metric is not going to be able to tell them apart. Aleatoric uncertainty we measure as the average entropy of the predictions across the ensemble, and it's highest when a model score sits at 1/2. So this measure is large when each model on its own is unsure. And this example is Bob, right, that we saw already. High average entropy flags exactly the ambiguity that lives in the data. And finally, epistemic uncertainty is the predictive variance across the ensemble, how much the score for the same person moves when we retrain. And this is Cat's case. Each model may be individually confident, but they land in different places, so the variance is high. And this is the component you can hope to reduce with more data or by selecting a different model class. So here's the first result that I'm going to show. There are many more results in the paper. I will just highlight a couple. And it answers the question that I asked you just now. Does getting imputation right guarantee getting the model right? And it does not, right? So if it did, you would see a trend here. And you see that this is essentially a scatter. Each point is an imputer on a data set. The left panel is MCAR, and the right is MNAR. On the x-axis, we see imputation quality, how well we reconstructed the missing values, and on the y-axis, F1 of the downstream model. If imputation quality tracked model performance, the point would climb from bottom left to top right. And instead, you can look at any vertical slice. At the same reconstruction quality, downstream performance ranges from poor to excellent. Mediocre imputers often support perfectly good models because a strong learner can compensate for imperfect fill-ins. And the same holds for fairness. Imputation fairness rarely predicts model fairness in the sense of disparities in accuracy between groups. So for this audience, of course, I should connect this to theory. There are important consistency results for impute then predict. Julie Josie will speak tomorrow. She and her colleagues showed that even simple imputation is consistent for prediction asymptotically. But our results live somewhere where these guarantees are silent. We work on finite samples, subgroups, stability, and missingness shift. So consistency tells you where you land in the limit on average. My plots show you what happens before you hit the limit, right? And this is what often happens in practice. So the practical upshot here is do not evaluate an imputer by reconstruction error alone and stop there. Evaluate end to end. Think about the entire pipeline. So now let me show you what happens under missingness shift. Everything here is one model. Here it happens to be random forest on one data set, diabetes. So any movement that you see comes from missingness alone and from the imputer. On the y-axis, fairness as the true positive rate difference, and lower is better. Each line is an imputer, and the x-axis is the training missingness rate. And the dashed line is the fairness we would get on fully observed data. The left panel is the no-shift case. MCAR at train and at test. The lines stay close together and close to the dashed baseline, to fairness on clean data. The choice of imputer matters, but behavior is tame and it's roughly predictable. Middle and right panels are the same imputers, but now the test mechanism is different from training, so there's a shift. MAR in the middle and MNAR on the right. Fairness degrades, and more importantly, it becomes erratic. The lines spread, cross, and jump, and the ranking of imputers changes as missingness rates change. There is no imputer here that you could have picked in advance and known that it would have worked for you under missingness shift. Deletion in blue is reliably among the worst, and this is the case for all of the experiments, essentially, that we did in this benchmark. So at least that lesson is easy, don't delete. And MNAR at test, the panel on the right, is the hardest case. And this is just as we would expect, right? Just as theory would predict. So the takeaway here is that if you validated your imputation choice under one missingness mechanism and then deploy under another, which is Anne's situation exactly, your fairness guarantees also go out the window with that. Let me collect the lessons for the first part of this talk. And these are, let me just open them up, that there is no single best imputer. The right choice depends on the mechanism of missingness, the model, and the metrics you care about. Missingness shift is real, and MNAR remains hard. Fairness degrades unpredictably when train and test mechanisms differ. Imputation quality does not, in most cases, predict model quality. And so we need to evaluate end-to-end on accuracy, fairness, and stability together. And the bottom line is the claim I started with, and that is imputation is modeling. So we should evaluate it the way that we evaluate other properties of our models. The results you just saw took about 30,000 pipelines, each profiled for accuracy, fairness, stability, and uncertainty, and both overall and in a whole bunch of groups, in a whole bunch of subsets of the data, including also intersections. And this is hard to engineer. It really takes deliberate engineering. And I want to give just a couple of minutes to this Virny project, because it's the measurement infrastructure that we have built, that we're using. I also use it to teach responsible AI. And it's an underappreciated research contribution in computer science and responsible AI, is the engineering effort that it takes. And we call this project Virny. As I already mentioned, it's led by Denis Herasimuk, who is part of the RAI for Ukraine program from the very start and is actually joining me at NYU as a PhD student this year, and I'm thrilled. So this is also involving a few other students from Kyiv and from Lviv. So the project has three components. Virny measures. It's a model-agnostic profiler of accuracy, fairness, stability, and uncertainty, the measures that I showed you, computed per group and for intersections of these groups. VirnyView inspects. It's an interactive model comparison and selection tool with constraints, trade-offs, and what I like to call nutritional labels, a kind of a dynamic documentation. And VirnyFlow optimizes. This is the most recent part of this project. It's a multi-objective pipeline optimization toolkit that works at scale and is driven by a user-defined evaluation protocol. And you will notice that there's a dashed arrow at the bottom. This is a loop. You look at what you measured, revise your objectives, and then you measure again. Evaluation drives optimization, not the other way around. And let me show you each piece very briefly. So this is the Virny component doing model selection on a benchmark dataset and task called ACS income. The user declares the constraints, and these are accuracy, equalized odds, it's a kind of a fairness constraint, and also label stability, both overall and as a ratio between groups. And here for the intersection of sex and race. And the bar chart that you see on your right is how many of some 12 candidate models survive each constraint and then combinations of constraints. Every model survives something and only 4 survive all constraints. That is the bar at the far right. And 2 things to notice here. One is that the stability constraints do actual real work. They do limit the set of models that come through the pipeline. This is a constraint-based selection protocol. It's not leaderboard based, right? It's not purely mechanical. The actual person designing these systems, the data scientist, specifies the constraints and can appreciate the trade-offs. And once they've narrowed down the set of models that are reasonable, they can go and profile each model in detail. So here I'm showing you again the stability and uncertainty component of the panel. This is the model nutritional label. And VirnyFlow closes this loop. And this is the hardest part of the system to engineer. It's on GitHub. Please use it. Let me know if you have any suggestions or encounter any issues. It doesn't just measure all of these properties. It optimizes for them jointly. Right? So the results that I showed you in the Shades-of-Null benchmark, we tuned our models under realistic deployment scenarios. We tuned them for F1. Here, what VirnyFlow allows you to do is actually tune for a combination of these criteria, including also tuning for stability. So on the left, you see the objective that drives everything. This is the evaluation protocol. The user declares the objectives with weights. And here we have F1 overall at a quarter, fairness disparity for sex race intersection at a half, and in the pink box, I have label stability at a quarter. And that protocol drives every layer of the optimizer. Bayesian optimization over pipeline configurations and cost-aware scheduling over which candidates to explore. And to our knowledge, this is the first system that can tune for model stability as an objective, rather than only measure it after the fact. And of course, as soon as you start tuning for stability, you need to do multi-criterion optimization, right? Because the most stable model is one that always gives the same answer, and that's useless. So that means that you always need to also bring in some notions of accuracy into the picture. And it also scales, which is the system's contribution here. So on the right, I'm showing you performance on 2.6 million rows and speed up climbing to about 31 times at 128 workers. Less important, but this is a comparison where we essentially beat AutoML systems that are out there. So let me make this concrete with a clinical case study, cardiovascular risk screening. We train the pipeline on the cohort where screening data is richest, and this is ages 55 to 64, right? These are patients whom we see at hospitals most frequently for cardiovascular risk. And then we deploy it on a younger cohort of patients. And here's what happens. F1 drops by 56% on the youngest cohort and by 20% on the middle one here. The lesson is the one you saw with missingness shift. What you validated is not what you deploy on. And both configurations here are on the Pareto frontier. And the system's job now is to surface the trade-off. Changing the weights here becomes a clinical decision, not an algorithmic one. Okay, so let me take stock of what I told you so far. Everything so far was about predictions, how data engineering choices change what the model predicts, how accurately, how fairly, how stably, and also how to measure and optimize all that together. But in high-stakes settings, the pipeline doesn't end at prediction. We owe people a justification, and increasingly the law requires that. So the natural question is, do data engineering choices that destabilize predictions also destabilize explanations that we produce? And this is the second part of my talk. In this part, and I know that I don't have half the time left, I have about 15 minutes, right, or 10 minutes, so I'll go quickly through this. But here, here I will discuss two lines of work that are about data engineering meeting interpretability. And here are pointers to some more work here. So to set up the objects we will be studying, we're talking about local feature-based explanations. Who knows things about these things so that I can skip or not skip the kind of quick intro? Okay, so I'll still do the intro, but I'll do it quickly. So this is a classic picture from the Lyme paper from 10 years ago, where we have a doctor using an explainer to see what the diagnosis should be for the patient, and the explainer tells the doctor which features drive the diagnosis of the flu. Sneeze and headache in green supported, and no fatigue in red argues against this being the flu. The doctor, not the model, makes the decision, but the explanation helps that collaboration. And notice that there's a question at the top here: what if the patient's ID appeared in that list? Then something upstream has gone wrong, probably that this is data leakage or a spurious feature being shown as part of the explanation. And this is how you might catch it with an explanation like this. So the workforce horse in this family is actually not Lyme, but it's SHAP. Shapley additive explanations. The model takes this patient here on the left, age 65, female, blood pressure 180, BMI 40, and outputs 0.4 for some task against a base rate of 0.1. SHAP distributes that difference among the features. Age contributes plus 0.4, sex minus 0.3, blood pressure and BMI are 0.1 each, and the contributions are Shapley values, so they add up to exactly the prediction of 0.4, and they carry the axiomatic properties of cooperative game theory, which is why we love them dearly, because we can understand them mathematically and reason about them rigorously. This is part of the reason that SHAP is very broadly used, both in development and in production, but also as part of regulatory compliance. And all of this rests on an important assumption, and that is the explanation itself reliably tells us which features actually matter. But what if this assumption was wrong? To ask that question precisely, we need to look at how these numbers are actually computed. So let me speed through this. This is just a very quick refresher. So we have a patient here with all 4 features present, and the model outputs 0.4. And I want to figure out how much BP, blood pressure, contributes. And so for that, I'm computing its marginal contribution. What changes when feature BP is present versus absent? And I'll tell you what I mean by that in a second, with this particular set of other features being held fixed. So we ask the model a second question. Now the same patient, but with BP removed. Now the output is 0.28, and this comparison is for one of the subsets of the other features, and we repeat this over many, many subsets. And then the difference, plus 0.12, is the marginal contribution of BP for this subset. And we average these differences over subsets with the Shapley weights from game theory, and you get the attribution, the phi value of BP. And this is the number that appears on the SHAP slide that I showed you. But there's a problem hiding here, and that is in the second row, and everything in the rest of this part of the talk essentially is based on that. The problem is that BP can't just be absent, right? Because a model is not going to know how to predict, so we need to fill it in somehow. How do we fill it in? What we do is that we look at the data. And there are many ways that people have done this. You can condition, you can just sample from the data set itself, but from a kind of a 100-mile zoom, you're going to look at background data, some real patients, and then you're going to be essentially sampling, picking up values from that background data and filling them in. And then you're going to be asking what the model's prediction is, and based on those numbers, you're going to derive the contribution of BP specifically in various subsets. So notice what just happened. There are 2 choices that I made. The first is what is the background data, and the second is how do I sample it to fill in these missing values. And the 2 claims that I'm about to make live in those choices precisely. So here's the main claim for part 2, and that is explanations inherit the uncertainty of the pipeline. And here, uncertainty is once again going to be due to feature engineering choices. And this is a project in which we explored this. We call it SHAP Attack for short. It's joint work with collaborators from NYU and KAIST. So let's take a look at this pipeline here. We start with raw data, and then we conduct feature engineering, followed by model training and prediction. And then we instantiate the SHAP explainer, and finally we produce an explanation. And the choice that I will locate in this pipeline is, of course, feature engineering. So I'm going to start with the simplest kind of feature engineering that there is. I will compute histograms of my values. And people just take defaults here. They don't really think about whether and how a histogram might impact things downstream. Long story short, here I'm giving you some ages of people and 3 common ways in which you can bucketize them. There is an equi-width histogram, equi-depth, and then there is a tuned histogram of a particular kind where I decide where I put the boundaries. And I have 12 people here. They're binned in different ways. And what's interesting is that if I take the same 46-year-old here, the pink dot, and I then represent them with the mean of the bucket into which they fall, their age, according to these representations, will be different, right? Obviously, 37, 39, and 55 is what they will be deemed. Now, here's a real instance from ACS income. This is a benchmark census data set. Here, I'm showing you feature importance, and specifically take a look at age here. This is the most important feature, where age is encoded as just a numerical value. And here, age is 30. And it comes out to be the most important feature. Now, you're a bank. You're giving an explanation to somebody as to why their loan was denied, and you say the most important feature was age. This is discriminatory. The bank is in trouble, right? So what's the bank going to want to do? They are going to want to give an explanation that makes sense, but where the age is not as important. And guess what? It's very easy for the bank to do this because they can pick a representation, a histogram that nobody usually asks them about. And here's one where I have 12 buckets of age. The median representing that age of 30 is 33, not even that far, and its importance is 6 right now, right? So no longer in trouble. That's the gist of this talk. This effect is systematic. How you bucketize your features, how you bucketize continuous features, how you combine categorical features matters. It can change the explanation drastically. I'm flipping through this because I'm running out of time. And you can use very simple Bayesian optimization as a malicious vendor to actually tune histogram bucket boundaries to degrade the importance of features that you don't want to come out on top. This is for categorical features, race. So you can do one versus all buckets, or you can represent each race in separate buckets, or you can combine them in different ways. Again, there's a very small number of choices here, even small number of combinations. You can find one that works really well for you. Here I'm showing how you can manipulate the importance of race in an explanation. So the lessons here are that feature engineering, the thing that no one thinks about, impacts explanations. It's not neutral. SHAP is sensitive to data representation. That sensitivity can be exploited adversarially, and so governance must include feature engineering, because an auditor is not going to be able to know what you did to your data unless this is being disclosed. So the bottom line is that here uncertainty is in a different sense. It's from choices that people make as data engineers, and it can be reduced, but not technically. The way to reduce it is actually by documenting this and disclosing this upfront. And 2 more minutes, if that's okay, or 3, yeah? 1? Okay. So there's also another piece here where I'm talking about how explanations can change simply due to randomness. Even if you change nothing about the model, the data point that you are measuring, and really anything at all, other than just producing the explanation again and again. And here's an example where I have 2 explanations on another credit data set. One of them says that credit amount, existing credit, and duration are the most important features, and the other one says saving status, checking status, and credit history. So here again, if a vendor is unhappy with the explanation they produce, they can flip a coin again and generate a different one. We call this explanation multiplicity. It's something that we quantify judiciously in our pipelines, and we advocate for transparency reports that would actually include explanation multiplicity in them that would allow you, as a consumer, as a person being impacted, to actually see how much to trust the explanation that you have received. So I'm going to give you just a report here. And the novelty here is how do we measure things, right? What are the baselines? What are some of the metrics that we use to say whether or not explanations agree or disagree? And the main point here is that if you use something like the L2 of the feature importances, it catches nothing. You need to look at something like what is the actual Jacquard distance between the top 3 features that everybody looks at of one explanation versus another. So the kinds of metrics that matter to people in practice are the ones that we should be measuring with here. This is a report, a stability report. And just 1 minute, right? Arbitrariness is bad. It's bad in practice, it can lead to disparities, and it's very often invisible. And in this talk, I talked about stability as a kind of a way to get at arbitrariness in decisions, aleatoric and epistemic. I showed that it exhibits very, very frequently in very standard scenarios that we have been looking at as the community. Error-based metrics, including error-based fairness metrics, don't catch this. So we actually need to get into the habit of measuring stability and uncertainty and displaying it and optimizing together with it. Arbitrariness is real and disparate. Why is this a problem normatively? It's because it actually gets back to the oldest principle of fairness, and this is procedural justice. Like cases should be treated alike. Machine learning strains this principle in a way that you all know. Many equally accurate models disagree on individual predictions. This is the Rashomon effect that we know about. But an unstable pipeline fails an even weaker test. No two like cases, not two like cases, the very same cases can actually lead to different predictions, different outcomes. And it's as if decisions were drawn from a hat. And arbitrariness is a problem when it's systematic. This is a due process issue. And it's also a problem when it impacts different demographic groups differently. It's a fairness issue. Decisions could be more arbitrary for one group than for another. And I talked about how arbitrariness enters upstream of decisions. And the law already leans on explanations. The law already requires disclosure, and it requires that we give people an opportunity for recourse. So unless we think about stability, unless we think about surfacing the kind of uncertainty, right, that our decisions bring into the world, we are not going to be helping people, and we are not going to be legally compliant. And here I'm giving some examples that the EU requires disclosure and recourse, the GDPR's right to an explanation, the AI Act, transparency and documentation duties. They all require us, the research community, to give them the tools to actually comply with these requirements. But there's no standard for what disclosure contains, and there's no safe to deploy. Disclosure itself can be arbitrary, and this is one of the issues that we don't think about. And also recourse can be less reliable as a result of this. So this, I think, is a call to action for us, both technically and in terms of real-world impacts. Thank you to my collaborators, very, very many of them, and to the sponsors. Yep.
Take some questions. Yes, please wait for the microphone to reach you.
Hi, thanks for the great talk. I very much agree with the conclusion that imputation is a very influential modeling choice. I have a question about the design of your experiments, especially the distribution shift part.
Yeah.
So if we allow the mechanism of missingness to change between training and test, there is no imputation methods that can do well on test, because whatever they have learned on train is allowed to be scrambled at test time. So why are, I don't quite see why are we blaming the imputer in these scenarios. So here is, so I think your examples of the clinical use case was quite clear. So if we have trained on old people and we are deploying on young people, I guess the question there is, why are we deploying in this cohort? And is the data, first, before deploying and optimizing anything, shouldn't we ask ourselves if the data supports this deployment? If we don't know, if there is a distribution shift, shouldn't we detect the shift first?
Yeah, so I wouldn't say that I'm blaming an imputer here, and this is an excellent question, right? I'm not advocating for any particular kind of an imputer or for any particular kind of a combination of imputer and architecture, right? What we're doing here is we're looking at what kinds of shifts can actually be detrimental to what kinds of metrics, right? So what you can do in practice, what you can do in production is unless you know that your data has shifted, you're not going to know when to act, right? So what you could do is you could try to take a sample of your data, try to validate, to bring this back into a supervised scenario, and then you can use some of this methodology to look at whether the metrics hold up and what the trade-offs are. So you can also look at more details here to understand, and I'm happy to talk about this offline as well, what kinds of shifts and what kinds of models and what kinds of imputers together are more robust, right? So what you can do when you're deploying also is in your particular scenario, you can think about what your data looks like, and you can try to run a couple of scenarios with this machinery. But unless you measure, there's nothing you can do, right? And so what I'm advocating for here is a kind of a judicious setup and a judicious measurement instrument. And there is no, these problems are not solved, right? A neural architecture is not just going to work magically, right? All of this is hard. It's not going to be less hard. And the other thing that's important here is we took a lot of time to actually design these scenarios that make sense. The practice in the literature that I've seen is just we go and we randomly infuse nulls. And that is not representative of any setup, right? So that's another lesson here, is think about what your data actually means and how might it change.
If there's another short question, we can take it, and then we'll move on to the break, and you're welcome to ask Julia offline.
Can I ask really quick, thanks for the excellent talk, Julia. Really quickly about some of the fairness metrics you touched on for your evaluation. So you like mentioned a bunch of things like differences in accuracy across groups or like equalized odds or things like this. And in the fairness literature, you know, one of the starting places for a lot of the discussions is that none of these particular metrics are, or they're not mutually satisfiable in general. Like that's like satisfying one will often involve sacrificing another. And some people take the conclusion or the implication of that to be that none of them are by themselves sufficient or even jointly sufficient to like say that a model is fair. And so I'm curious if how that manifested in your study here, or what your recommendations would be in light of that.
Yeah, so this is a loaded question, and I do quite a bit of work on fairness, and in fact, Dan, yes, there is this, I wouldn't say it's a misconception, it's a little bit deliberate also, is that because we have these fairness incompatibility results, that means that we just can't do anything about fairness and we should throw it all out the window. The incompatibility results, they hold in a very strict, clear sense that in practice people usually don't care about. You can actually give yourselves margins to satisfy these metrics up to, I don't know, 10%, 5%. And these margins are not dictated by you, the data scientist, they're dictated by what's acceptable in the law, for example. But what a methodology such as mine gives you is that it allows you to actually look at where are these pockets of compatibility or incompatibility, right? So let's maybe zoom in here very quickly. This was the Virny component, where I told you that I'm stating some of my criteria. And so here I'm not saying, and be exactly fair on equal false positive rates across all of these groups. I'm saying here is a margin that I'm comfortable with. Show me what models are you able to find that fall within that margin. So we absolutely must make an effort to understand what the trade-offs are between these metrics. And they, of course, are very difficult to optimize jointly mathematically because they have very different properties. Think about a metric like, just raw accuracy versus a fraction, a ratio of false positive rates between men and women, for example, right? I mean, these are just, the second one is not at all convex, so how are we going to optimize together? So this is where the difficulty is. And the other twist that we're adding here is that some decisions can be less stable than others for some groups, right? Because you might have just less data for a particular demographic group, for example. So you might be learning something that is arbitrary. One day you get the loan, the next day you don't get the loan. And this is not something that we've seen measured anywhere. And that's another property that's very important to look at. So yes, things are hard. But that doesn't mean that we should give up on them. It means that we should work on them more and that we should be developing joint optimization frameworks that go beyond what I showed you. Because here, ultimately, what I have is an additive optimization criterion that assigns weights to particular metrics and then optimizes that jointly. But you need something more complex. You need to condition on some metrics and then walk the Pareto frontier with respect to the others. So there's a lot of work to be done here. And Gen AI won't solve it for us, obviously. So, bingo. Yeah.
Thank you, Julia. Let's thank Julia one more time for
Thanks very much. Happy to share my slides. I don't know how to best do it, but yeah.